Hi, I'm Toni, developer of Semantic Web Technologies at Wolfram, as well as the Entity Framework. Today, I'm going to demonstrate some new functionality in version 12 of the Wolfram language, together with Andrew, who's going to monitor your questions and maybe relay them to me. Yeah? So first of all, what is all of that about? What is the semantic web? Well, I don't want to give a definition of that now, but instead, I'm going to show you some examples, and from that, maybe it will become apparent what we are talking about. So, like in the other sessions that we had so far, I'm going to present this page, which is, well, made to demonstrate this new functionality. Yeah. And I'm going to go through the examples and maybe give some wisdom as a developer that maybe is not apparent when you just read those examples. Yeah. So we have a few, we have those examples grouped more or less by functionality, but in this case, it's a little bit, well, the first row is about basic functionality that everybody would be using, yeah? And the second one is about more advanced features. The third row goes into some details, and then there are some examples that show applications, and maybe there I will highlight why this technology is so great. And in the last examples, well, I'm going to apply this technology to entities. So we already have given a talk about entities some time ago. So here we're going to make the connection a little bit deeper. Yeah. So, but before starting, let's go to a website where I'm going to show you certain things, and later you will understand why this technology that we are developing here is so important. So let's go to one of my favorite websites at the moment, Wikidata. I'll come back to the examples in a moment. Wikidata is a database that stores statements about items. In this case, over 50 million items. And I can go, for instance, to the item, let's say chemical, caffeine, a chemical compound. Yeah. And on this page, you see it has a lot of data. Already at the beginning, it has a lot of synonyms. Yeah. It says what it is an instance of. So, for instance, you see it's a chemical compound. It has an image, and it has a chemical formula. Yeah? And you might be wondering, how do I get to this data? Before the semantic web, your mind would probably start racing, say, easy, I can just import this website, look at its source code, and maybe figure out how the data is stored there, write a parser. And a day later, you would be able to use the data in this page. Yeah? But now everything is much easier. You just send a request that says, give me linked data of that, and import it, and it's a one-liner. I'm going to show that later in detail, but let's continue with this example. Yeah? Let's say I want to find all the chemicals that have a certain substructure. How would I have done that in the early days before the semantic web? Well, probably I would have tried to download all the websites and then later look for the substructure in all of the chemicals that I happen to find. But this, for 50 million items, as you see here, this might be a long and difficult task. So what else can we do to solve our task? Wikidata has a query interface at query.wikidata.org. Here I can write a query to query not only this data item, but all the data items that Wikidata knows about. Yeah? And what kind of query language is? It's SPARQL. Yeah? So the semantic web is defined by certain standards, namely a data model, which is called RDF, the Resource Description Framework, which is a graph-like data model, together with a query language called SPARQL. And we are going to query Wikidata with SPARQL. I'm just going to write a simple query, and then we are going to come back to the examples. For instance, let's count the triples in Wikidata. So when I click the play button, it's executing the query and it's giving me a large number. Those are all the triples or the number of all the triples in Wikidata. And maybe if you know SQL, the select clause might look familiar. Yeah? So here you write some variables that you're interested in. But this part is different. Here, I'm writing a so-called triple pattern. Yeah? And in this case, this triple pattern contains variables. Variables are the things that start with a question mark. Yeah? And in this case, I'm not placing any restrictions. I'm doing that by using a variable in all places of this triple. So that means this one is going to match every triple in Wikidata, yeah? And then I'm just counting them. So later we're going to see more complicated questions, but just about the principle of how this works, how would you now get this data into the Wolfram language? Yeah, you might be wondering, well, I can just copy this URL and then try to import it. I might have to fiddle around a little bit. Maybe there's even a hidden parameter that allows me to import it in JSON. Yeah. But that's not what we're going to do. Let's see how in the Wolfram language we can send a query to Wikidata and get the result back without any setup. The only thing that we have to do is we load graph store, in which all the functionality that I'm going to talk about today is contained. That means symbols for representing RDF data, as well as query primitives. Once I load graph store, I get access to a function called SPARQL execute, and it takes a so-called SPARQL endpoint URL, as well as a query. And now I can execute it, and I see I get a similar result as before. Let's execute it again. Oh, we see, since the first execution, the number has already changed. So the result is of the form of a list of associations. So as a Wolfram language programmer, you might know the associations. Yeah? They are basically a list of rules. And in this case, it's from variable names to values. And in this case, I just have one result. Yeah? So with this little motivation, let's go to some examples. The first example basically repeats what I just did. Yeah? So given a SPARQL endpoint, and there are multiple out there in the internet, and later we are going to see how many potentially. The only thing that you need to, for instance, ask Wikidata about the highest mountain is specify the endpoint, specify a query that asks for the highest mountain, and then execute it using SPARQL execute. Yeah. Before going to this example, let's give for everybody who doesn't know RDF or SPARQL at all a quick introduction. Yeah? I'm going to try to give a crash course on one slide of RDF. So in RDF, everything is about triples. Yeah? Here I have a document, and that's something that you can find in this form on the internet, for instance, or you can generate it yourself, that makes a few statements. Yeah? And just by looking at it, you might already be able to see what it says. Here I have a thing that starts with a colon that says Tom, and then hair color and blue. And then there's a dot. It nearly looks like a sentence. And that's basically the idea of RDF. Yeah? You have a subject, a predicate, and an object. And this sentence makes the statement that Tom's hair color is blue. And then there's another sentence, Tom's mother is Anna. And then Anna's hair color is orange. Yeah? So that's the whole idea of RDF. It's so simple and powerful. You just add triples, yeah, to form a so-called RDF dataset. Yeah? In this case, it's an RDF graph, but if you have multiple graphs, they form a so-called RDF dataset. And now we can just import this document. In this case, it's a turtle document. Yeah? And the result is something that said RDF store. Yeah? An RDF store is an in-memory representation of RDF data. So you can create something like this either by importing one or creating one yourself. We're going to see both of that later. Yeah, and as I said, an RDF store usually contains one default graph. Yeah, in case those triples. Yeah, and I can access this default graph using that property. Yeah? And you can see that's the Wolfram language representation of a triple. It says RDF triple, and then a few IRIs. Yeah, in this case, Tom, hair color, and well, a literal. But in general, an RDF triple consists of few IIs. By the way, what are IIs? Yeah. So this thing that you see here in the address bar, that's called URL. Yeah? And URL stands for Uniform Resource Locator. Yeah. So important, L for locator. A superset of those URLs are URIs, where instead of locator, you use identifier. Those are more general concepts. For instance, you can have a different scheme instead of HTTP, the thing that you don't see here in this browser. You use, say, ISBN, which is a famous way to identify, for instance, books. Yeah, and now the next generalization of URIs are IRIs, where the first I stands for internationalized. That just means that in those kind of addresses, you can also use international characters, not just English ones. So, and then the idea is that every object that you're talking about, you create an IRI yourself. In this case, I used an example namespace. Yeah? But if you create your database, well, maybe you choose a different one, or you reuse existing IIs for your things. And then you make statements of that form. And now that we have in memory our RDF store, let's execute a query against that store. Yeah. And there's a new function. By the way, a graph store contains over 30 new symbols. Yeah. Some of them needed for representing RDF data, like the RDF triple and the RDF store, also the idea of an II, as well as query operators and primitives. In this case here, I have a SPARQL query operator. Yeah? Maybe you know the function query, yeah? which is our symbolic representation for querying hierarchical data. It's basically an encapsulation of the dataset query language. Yeah? The great thing about this thing is that you cannot apply just to dataset, but to arbitrary expressions. Yeah? So we are following a similar design with the SPARQL query operator. Yeah? And you can have a symbolic representation of SPARQL inside that operator, but that's what I'm going to show later. For the beginning, let's use a SPARQL query string, which sometimes is easier to read. Yeah? And how do you read this query? Well, you have a select clause, as we've seen before. In this case, I'm selecting everything. I'm not aggregating or anything. And then here's a triple pattern. What is a triple pattern? A triple pattern is basically a triple in which variables can appear. Yeah? In this case, I'm trying to look for all triples that have in the subject position Tom, and in the predicate position hair color, and in the object position, well, anything. And whatever the value is, yeah, I'm calling it color. Yeah? So you see, you can query the store and figure out that Tom's hair color is blue. Now let's do a fancy query. We want to know what Tom's mother is, and for the mother, the hair color. And I have to move. No. Like that. And so, and you can see that, well, we get bindings for two variables. Yeah, so this is, we were filling out a slot for, or we were finding variables or values that match that variable, and then continue from there to find the color. Imagine doing that using relational databases, in which you would probably have one table representing the relationship has mother and has hair color. So you would have to do a self-join on that predicate. Yeah. Here you don't have to know anything about it. You just write your sentence and place variables wherever you want to figure something out. That's the idea of SPARQL. Yeah. So now that we have seen a little overview of RDF and SPARQL, let's continue with the examples. So we've seen it already. So the representation of RDF data. I'll drink something. So, as I said, in RDF, everything is about describing resources. And those resources are identified using IRIs. And now I want to create a little RDF store from scratch. So I'm looking for a vocabulary that I can reuse. And it's always good to reuse existing vocabulary because of the network effect. What is the network effect? Well, it just means that the more people use a certain vocabulary, the more tool support will be there for recognizing things in that vocabulary. Yeah. So only if you're working in a new area for which no vocabulary exists, well, then create your own. Otherwise, try to find one that already fits your needs. Yeah. In this case, I'm reusing vocabulary, the basic RDF vocabulary, which unfortunately has this very long and verbose IRI, which I have not memorized yet. So that's why I'm introducing those small utilities to create those IRIs. Yeah? So this is the RDF namespace, which has basic information like the type, yeah, of a resource. Yeah? So you can group resources into classes. And those classes are themselves resources. So everything is an IRI, except maybe literals and blank notes, but we might see that later. And then there's the famous schema vocabulary. And for this example, I'm just creating an example IRI, an example namespace. Yeah? And we want to store data about a book. Yeah. So we make a triple that says that thing is of type book, and its Hungarian name is that one, or Növer. And we say the author. And here you see one thing, the author is a string. Ideally, you would not use a string here. You would maybe go to Wikidata, yeah, find the author, yeah, and use that concept URI in this data. Why would that be useful? Because if you say use that data to make a summary box on your website about your favorite books, say, then you could follow that IRI and, for instance, retrieve an image or some other important data. Yeah? So it's always great to link your data to other data sets that might provide useful information. So you don't have to duplicate the effort. Yeah? And now that I have this RDF store, I can, for instance, to publish it, yeah, export it in one of the many RDF formats. Yeah? One common format is Turtle, yeah, and it's useful because it has some abbreviations. For instance, it groups all the triples about the same subject, yeah, into so-called predicate object lists. But maybe more on formats later. So that one I already mentioned. Yeah. So if you have an RDF store in memory, you can immediately execute queries against this RDF store. How's that even possible? Well, we can understand this query string, and we have an evaluator built into the language, yeah? And we can directly execute this query onto the store. So no database setup required. Just import it and do your analysis locally. Well, a little developer note, maybe if you're working with small stores, let's say stores that load within a few minutes, then it's fine to do it in the Wolfram language. If you're doing something much larger than that, maybe then you should set up your dedicated SPARQL endpoint and use the Wolfram language as an interface to that SPARQL endpoint. Maybe your local SPARQL endpoint. So in this case, I have a data about fruit, and I'm finding all of the fruits in it. Yeah. And the other important concept is importing RDF data. So we have seen export, and now we can import. Let's say the Library of Congress publishes data about genre in RDF, yeah? And you can import it in one line. Yeah? It's a remote file compressed as zip, but our importer handles that. It automatically uncompresses it and imports it in the right format. So you get a big RDF store out. And what's the first thing that you would do when you get a new RDF store? Well, you might read the documentation to figure out what vocabulary they're using, but you can also simply explore it yourself. In this case, I wrote a simple query that extracts all the properties. How does this query look like? Well, it's finding all the triples and selecting the distinct values for P. That means the things in the predicate position. And I see that there are, say, 30 properties, more or less. Amongst those properties, there's a property called has broader authority. So because this is about genres, I want to make a graph of those genres. Yeah? Nothing too scientific, just make a nice picture. Yeah? So I start with a genre and find a broader authority and call it genre parent. Yeah? And then I can make a graph out of it. So the little bit more complicated query, just to show you the capabilities of SPARQL, is to find all the top genres. And how do we do that? First, we find all of the genres, and then we exclude solutions for which the genre has a parent. Yeah? So we remove those that have a parent. And what remains are the top genres. Yeah? Then we can make a word cloud out of it. That completes the first row of basic functionality. That means querying remote or local SPARQL or RDF data and importing and exporting RDF data. Now, advanced features. Symbolic SPARQL, which is maybe one of the most powerful aspects of the whole project. Imagine you're not using a query interface to manually writing queries like this, but you have a program that is maybe data-driven or that generates a query, say, from a user interface. Then you might want to build up the query from small pieces, and you might not want to worry about how do you correctly string join all of the little parts together. Yeah? That's why we have a symbolic representation. And this symbolic representation works wherever you would otherwise be able to write a query string. So they work interchangeably. So you don't have to worry about joining correctly those things, doing type conversions. Yeah? For instance, how to represent an integer in certain formats. Well, that's all done for you. And in this little example, maybe I can evaluate that for you. Yeah, I have here. So again, data about fruits, yeah, and the example namespace. Now, what I want to do is basically find color and shapes of fruits. So I define a color pattern, yeah, and that's basically a triple pattern, yeah, that has certain variables, yeah. The predicate color is fixed, but you vary over all the subjects and objects. And then you also define a shape pattern. Again, the shape is fixed, and you vary over all the fruits and shapes. And then you combine those patterns into a so-called group graph pattern. Yeah? If it were just triple patterns, it's called basic graph pattern. But in this case, I want the color of all the fruits in that store. And optionally the shape. And when I evaluate it, well, I get that. I get that a strawberry is red and round, and a banana is yellow, and I don't know the shape. What happens if I leave out the optional pattern? Well, I get just the first solution. So optional is a very useful feature, but SPARQL has many more features, and we are going to see some of them on our journey through those examples. Like a good query language, SPARQL also has an update language, yeah, which means you can request data to be changed either on a SPARQL endpoint that allows you to write to it, or your local data. And in this example, we start with an old data set about planets. Now we look into it by writing a SPARQL query to find all the planets. And we see, oh no, Pluto is still a planet. So it's easy to fix that by just writing a SPARQL update request. Yeah? It consists of two parts. Yeah? It deletes the triple that states that Pluto is a planet, and it inserts a triple that says Pluto is now a minor planet. Yeah? And you simply apply that update request to your store, and you get a new store. Yeah? And in this case, I place this new store in per variable. And note that this one was an update string, but as for queries, you might want you might want to generate them programmatically. So there's a symbolic representation of updates too. Yeah? In this case, I want to add an approximate volume to each of the planets. So how would I do that? Let's first see the insert operator. Well, it takes a pattern of triples to match and a template of triples to insert. Yeah? And the pattern is a radius pattern for each object. I ask for the radius. And the volume basically consists of the radius processed appropriately to get the volume. Yeah? And then I can look into this new store and I see that, well, I have in addition to the radius now also the volume. Now a very important use case that I hinted at earlier. Maybe I have a slide for that. Yes. So now imagine that you find a website that has wonderful data that you would like to use. Yeah? In the case of Wikidata, you have a SPARQL endpoint, but not every organization can run a SPARQL endpoint. Yeah? But can you still use semantic web technologies to access the data? In this case, I'm looking at MusicBrainz, which stores very detailed information about albums, or in their terminology, releases. Yeah? In this case, I'm looking at a release about Tango by Francisco Canaro. Yeah? And I want to extract the list of songs in that CD. Yeah? You could, of course, write or try to write a parser for the data, but we can equally well request linked data. And how do we do that? First, we create a request that says, I accept JSON LD. This is just one of the possible RDF serializations. Yeah? You can also specify multiple accept headers if you, and then your server might just choose the one that it supports. Yeah? And then we execute this request and say, please import it in JSON LD. By the way, the answer of this request contains already the information that this is JSON LD, and URL execute at the moment does not honor the return type in most cases, but this is under discussion, and maybe at some point I can just drop this to make it even easier. Yeah, but for the moment we need to specify, yes, what's coming back, please import it as JSON LD. So we got again our RDF store in just 2 lines of code, yeah, that contains all the information about track information. And then we can look, for instance, at the properties, and we can see, it's using schema vocabulary. So let's introduce a shortcut to create those schema IIs and look up for each track the track number and the name. Yeah. So the track there's a question whether couldn't the IIs be auto-mapped to entities to reduce the range of objects in Wolfram language? I'm going to make a connection to entities later. Let's continue first with the basics. Because Mapping between entities and IIs, that's an advanced topic. Yeah, that's pretty experimental at the moment. Yeah. So to continue with that example, yeah, here we retrieved track information from our album, and we see each track has a IRI assigned to it. It's actually a recording. And let me show you something. I can click on that and I go to a human readable representation of that recording. Yeah? So I can get all kind of information, for instance, on which release does it appear? Who are the singers? Oh, and it even says when it was recorded. So a lot of detailed information. Yeah? I can equally well import data about that recording, but that's not what I want to do now because you get the idea, I think. So here is the name of the track and here the number. And I see it's a string in a certain format, so I can just post-process it a little bit to get finally the track list. Easy. Let's continue with one important concept that goes a little bit out of that row, but it's a very important thing. As you might know, the semantic web is based on standards. One of them is the standard suite of RDF that just concerns itself with the representation of RDF and includes standards like the semantics of RDF, as well as certain import and export formats. Yeah? And those standards are open and free, which means that everybody can and is encouraged to implement those standards. The same goes for SPARQL, which is the query language of RDF, which is also open and free, so everybody is encouraged to implement it. And that's just what we did. So if you create RDF data, you don't have to worry about login. You can simply export it, and every other tool that supports RDF can import it. Yeah? So our goal is to be a very nice tool for working with RDF data, but you won't be forced to use it. It's just if you like it. And yeah, that's what standard compliance is about. But how do we achieve standard compliance? So the standard organization, the World Wide Web Consortium, as well as some community groups are maintaining test suites for various of their standards. And here you can see the URL of the RDF test suite. And this contains tests for RDF, SPARQL, OWL, and so on. Yeah? And I've seen a few questions on the internet asking, how do you actually run those tests? So for certain languages, there are test runners. I'm just going to show you how to do that in the Wolfram language. Yeah, this seems like a long example, but it's just long because I'm going to explain in very detailed how you look around those tests, and the actual code to do it is pretty short. Yeah. So first, you just download and extract the archive of tests, yeah, and then you can look around the structure a little bit, but you'll figure out that there are various directories and subdirectories. Yeah, in this case, I'm going into the SPARQL 1.1 test directory, which further is subdivided into areas of SPARQL because it contains a lot of features. Yeah, in this case, I'm looking at the aggregates. Yeah, and the aggregate manifest file contains information about the tests. So to even start running tests, of course, you can always hack something together. You can do string processing on those manifests, and yeah. But to do it properly, and that's what we want to do here, is to import this manifest file given in Turtle as an RDF store, then extract the data using SPARQL and just run the queries. Yeah? So to get a feel for how this manifest file looks like, you can see here, you can use snippet to pick into it. Snippet gives you some, a part of that file. In this case, it's like a standard Turtle file. It starts with some prefixes, which define how IRIs are shortened for readability or for space. Yeah. Going further in the file a little bit, you see, well, a definition of the manifest and its entries. So these egg 1, Act 2. Those are the actual tests. And if you go further down, here you see one actual test defined, yeah, using turtle syntax. Now you say Act 1 is of type query evaluation test. In the test a name. It even lists the feature that it's concerned with. Yeah, has a comment. One important field is the approval, because there might be various ways in which tests are contributed, and some are approved by the working group while the working group is still active. Others might be contributed later. Yeah. So here you even have information about when and where this test was approved. Yeah, and then here the important information that we need for processing later, it's the action, which consists of a query and the data that you apply the query to, and an expected result. And now we are still not running the tests. Just one more little look at the data. We're defining some prefixes to write a symbolic query that extracts all of the test types. And how do we do that? One curious thing about RDF is that it has support for lists in the sense of linked lists. Here you can see a linked list that starts with this brace and then lists all of the elements. Yeah. Why linked list? Well, the entries basically has as object a blank node which links to its first element and the rest. And that element, which is the object of rest, then links to its first element and the rest. Yeah. So then how do you navigate such a linked list structure? Yeah. Here's an example of how you can do it. Now again, a symbolic query, just to show you a little bit the power of symbolic SPARQL. Yeah. You start anywhere, go along entries, then go 0 or more times along rest, and from that node you take the first element and the type of it, yeah, to find all of the types. Then there's an aggregate operator that you apply directly afterwards. You group by type, project out the type, and count all of them. And you see in the aggregate manifest, you have 23 evaluation tests and 5 negative syntax tests. We want to run the evaluation tests. Yeah? So let's extract the information. Yeah? So we find all the evaluation tests, the query, and the data, and the result. And, well, this is unfortunately small. But yeah, you can see, here's a test, for instance, Egg1. Yeah, I'm just looking at the first one in that list, but later we're going to run all. The action, as I said, is a blank node. Here you have the query. Yeah, you see it's a file ending in .rq. That's a file containing the query. And luckily, we have an importer for SPARQL queries to its symbolic representation, so we can just import that. Yeah. The data is a turtle file. The result is an SRX file, which stands for SPARQL results in XML. There's also SPARQL results in JSON. So a SPARQL endpoint could return any of them. So of course, we have importers as well as exporters for those formats too. But now finally, let's go to actually running the tests. And it's just that little piece of code. You import the query, apply the query to the data, which is an IRI, so the query evaluator automatically retrieves it, in this case from my file system, because it's a local file. We import the result and then we compare it. And here's the little comparison function, because as you've seen, the results, in this case, we don't use any sort by. We are not sorting the results, so they could be in any order. This is not specified if you don't specify an order. So we sort the keys, and then after sorting the keys, we sort the things. So, and you can see all the tests are passing. And that's very encouraging. Yeah? And of course, we ran all of those tests. Yeah? But it was tough bootstrapping to even be able to properly run the test, because we needed importers for the queries, a symbolic representation for them to map the imported thing to. Then importers for the formats, yeah, the data formats as well as the result formats. Yeah. We needed support for many features of SPARQL to, for instance, use the property path Yeah. But now all of those tests, yeah, can be run from the Wolfram language. Yeah. You can even use the Wolfram language using that example to drive test runners for other software that want to implement SPARQL or RDF support. So maybe I'll ask Andrew whether there are any questions so far.
No, I think just the one about the IRIs and how they relate to entities.
Yes. Okay, I'll come back to it in a moment. By the way, we are 40% through at 80% of the time, but I don't think there's a fixed limit, right? Well, let's continue with some details. Yeah. For instance, about converters. So this row is about converters, and I'm going to look at some of the examples quickly. So one of the possible serializations of RDF is n triples. That's the simplest format of all, and it's also pretty verbose. So sometimes you might want to write n triples because the application that's processing your data maybe doesn't want to do too complicated processing like it is needed for JSON LD or Turtle or RDF XML. So that's a nice format for simple applications. But for other applications, you might want to save space or make it more readable. Using our new function file convert, you can simply convert it from n triples, say, to Turtle. As I mentioned before, Turtle has an advantage that, for instance, it groups triples according to their subject, and even subject and predicate pairs. You see this colon and semicolon, and here the dot. Unfortunately, using file convert, you can't currently specify options for import or export. Otherwise, you could even specify the prefixes here. Yeah. But luckily, file convert is still marked as experimental, and I already filed a suggestion, so maybe this is going to improve. But anyway, it's just a convenience. You can always import the file and export it again using export, and then, of course, you can specify prefixes. Another useful format is JSON LD, which is a JSON-based format. And yet another one that is there because, well, for historical reasons, is RDF XML, which is an XML-based format. I probably wouldn't produce too much data in that format, but to maximize interoperability, of course, we want to support all the relevant formats. And this one was actually the first one that was mandatory to support by RDF processors. So, of course, we support it. But it looks pretty verbose. Also, for instance, the OWL test suite contains RDF XML encoded tests. So it's great we support it for future work. Another option that you've already seen, for instance, in Turtle, if you just export the file, you get a nice grouping. Yeah? But if you also specify the prefixes, all those IRIs, for instance, this long RDF schema, the thing is written shortly RDF colon schema. Yeah? And again, about JSON LD. So let's assume you have this nicely prepared JSON file about books, and it's using nice keys, nice short keys, name, author, and image. It's books about physics, I think. Yeah. And when you import that, you can always import it as raw JSON, which will give you a nested list or association. Yeah? But if you specify an expand context and name, author, and image are in the context of schema, then you can immediately upgrade this file to linked data, by using the JSON LD importer and specifying, well, this context. Yeah? And now that you have RDF stored, you can export it to another format, or, as in this case, use SPARQL to query it In this case, I'm going to find all the books whose author name is Kip Thorne. Yeah? Or here another one. For the book Gravitation, which I read in part when I was studying physics, yeah, you can find the image and import it. Or as I said, you can export the file as perfect. And now a very powerful feature. You have seen so far both SPARQL query strings as well as symbolic SPARQL. Yeah. And how do you go from one to the other? Of course, you can read the documentation. There are more than 30 new symbols, and then you will learn with time how to write queries. There's actually some nice documentation for each of the symbols. For instance, you can look at SPARQL select, and then you see a lot of examples of how to use it. And to help with reviewing that documentation. So thank you. Now, let's say you have a website, in this case, the example queries of Wikidata, and all of them are obviously strings, and you want to know how this string would look like in symbolic SPARQL. Yeah. You just take that query string and import it using import string, and the format is SPARQL query. Well, I just see that this one is not as simple as it could be, but that's already fixed for the next version. Yeah? But what you can see, if you can see that well, is it has had a SPARQL query, and it's a right composition of a select query and an aggregate. It's basically what you see here. Yeah? And now let's execute the query. Yeah? So we again specify our SPARQL endpoint and execute the query string. We can also execute a symbolic query, and it has exactly the same effect, except that, of course, the size of Wikidata changed. And also the number of humans that Wikidata knows about changed during the two requests. And even the symbolic query, you can go back to a SPARQL query string, and you can see that it's very nicely formatted. Yeah. That concludes the details about converters, and let's go to some examples. Here's an example that shows the power of the semantic web, or at least an aspect of it. We want to find theaters around a location to make a map. Yeah. And this query consists of a few parts, and we're going to use the symbolic representation of SPARQL so that we can parameterize the query and later change the parameters. Yeah? In this case, Wikidata offers a service that allows you to query items given a center and a radius. Yeah? And then it produces bindings for a place and at the location. Yeah? Yeah. So the place variable will later contain the items, and this variable will contain the location. Yeah. Once we have those items, they are IIs, as you will probably know, then we also need the labels. So we could use the RDF schema label vocabulary, but also Wikidata has a label service that simplifies things in certain cases, so we'll just use that. And then we also have a type query that says, for a place, find all the things that are an instance of potential subclass of something with a label or alternative label that, in this case, theater or cinema. Yeah. And now I just group all of those things. Yeah, I want to find things of type theater around Madrid, 1 kilometer, and the labels, yeah, and get those places. To retrieve all of the labels, you know, places is a list of associations. I just get all of them, and for each association, extract the place label, and I see here a list of results. Well, that one was evaluated some time ago. Probably now it's going to contain more. Yeah. But now here comes a curious thing. Yeah? If you look at the location, yeah? What are we doing here? We're taking their places, extracting the locations, and making a tooltip of the place label around the locations. Yeah? But then if you look at the points, we can see that Well, they are actually points wrapping a geoposition. How's that even possible? Well, the great thing about the semantic web is that everything has a well-defined meaning. Even data values, also known as literals. So they consist of a string and a data type. The data type is an II, which defines the meaning of the string. And in this case, Wikidata returned a literal of a well-known data type that the Wolfram language knew automatically how to map to its built-in primitives. In this case, it was a geoliteral, and this is the Wolfram language to represent it. It's at that position, and it's representing a point and not a disk, for instance. And then I can use geographics to plot the points. The only thing that I really need is apply geographics to the points. All the rest is just styling. So you see how much the semantic web facilitates data integration. You don't have to worry about this conversion if your data provider uses well-known IIs, well-known data types. Well, I'm going to skip that example, I think, because I don't know so much about biology. But in this case, we were retrieving gene transcript positions from a SPARQL endpoint of the European Bioinformatics Institute. Well, if you're interested, you can try to read the SPARQL query. On this screen, it's not formatted nicely. But we are working on making the symbolic SPARQL queries easier to read and write. So here is something that seems very easy at first, because what do I want to do? I want to build a Tango Explorer, but what does that mean? I just want to I want to find tangos in Wikidata, and for each of them, display their composer and their lyricist, and potentially an audio recording. But there's one problem. So each tango could be composed by multiple composers. It could even have multiple lyricists and multiple recordings. So when you retrieve them, you get all the combinations. So in your result set, you might not get one tango per your tango might appear in multiple results. So that's why this turns out to be much more complicated. But the solution that you will see here is very generally applicable to different problems, and I haven't invented that. There are various places in which this technique is used over the internet, but I'm going to explain it here for a moment. First, I want to find songs, and I do that by starting with a thing that is an instance of something that's potentially a subclass of a subclass, see the variable length pattern here, a song. And for the song, I want to get a Spanish label. And I also want to find the genre, something that is of an instance of a potential subclass of tango. And then the composers, together with the Spanish label, the lyricist with the Spanish label, and, well, in audio. And then I compose the whole query, trying to find songs of genre tango together with the composer. Not all tangos have lyrics, that's why I make the lyricist optional, and also the audio. But then I need something more. As I said, each tango could have multiple composers. So I'm grouping the songs by song and also by audio, but let's not worry about that either. And then concatenating the different composer labels, the lyricist labels, and then composing the select query with the aggregate. Once I evaluate it, I get a data set that I can query using the query language of data set. Before I mentioned query. And for instance, in this data set, I can find all the rows and project the song label and composers. So I see here a list of songs together with the composers. And then I can use the full power of the query language. For instance, find things find songs whose composer contains Gardel, and give me the name of the song and the lyricist. Or I can even make a little explorer that shows me the songs together with a clickable link, to where I can listen to that song. Those should be in the public domain by now, because those are really old tangos. And maybe I'm going to skip that example. Well, it's just a simple example in which I retrieved all the SPARQL endpoints that Wikidata knew about, and then sent them test questions, and see whether I get the correct answer, and then showed which of them worked well. And when I tried this yesterday, there were already 10 more of them. But we are going to skip that because it takes a minute to run. Now let's go to the last row, which means SPARQL. This powerful query language, why can't we just apply to entities? So maybe I have this example here. So let's start with how you would traditionally work with entities. So you have your entity and you have your property. You apply the entity to the property to get a result. For instance, here I'm asking for the capital city of Germany. Using SPARQL, I can do the same query, and it looks a little bit more complicated. You can consider entities to be virtually of the form entity property value. And now in this SPARQL query, I'm just going to virtually, oh, by the way, what does virtually mean? Of course, you can always form an RDF store by looking at all combinations of entity properties and generating all of the triples of that form. And then you can apply SPARQL query to it. But if you apply the query to an entity domain directly, well, you might get a fast evaluation, because those queries, or a large class of them, can be translated to more efficient entity queries that don't require you to download all the data. So in this case, I'm asking for all the triples in this RDF view of those entities, that have in the subject position Germany and the predicate position in the capital city. Well, here where I go, and I get the same result in the typical SPARQL result style. Now, let's do something more fancy. We want to know the population of the capital city of Germany. Well, again, doable using entities, because that thing evaluates to Berlin, I guess, and from Berlin we can get this population. In SPARQL, you would use a property path that starts at Germany, continues along the capital city and the city population to the population. Same result. Now it's getting tricky. If you want to do a reverse query, we have new functionality for filtering entities, and that actually supports this kind of construct. And filtered entity class, you can give it a type that you want to start with, and then the condition. In this case, you want to find all the countries whose capital city population is greater than 10 million. And this seems to be the result. If you want to do but well, you don't see directly what the value actually is. If you wanted to do that, how would you do it? Let's say and define a new property. What I'm trying to do now is to get the same result, but together with the values of that capital city population. And you have already probably seen our presentation about entity queries, but here's another quick example. And now you can nest that with a filter entity class. Where you say greater than that number. And then you can copy, let's see whether I did that right. Well, I'm not going to show that now. Well, using SPARQL, you can get the result easily by simply making the population a variable, constraining it, and then it's projected out here. Maybe one more example. Aggregates for entities. Well, we have aggregated entity class. That's how you can aggregate entities. But SPARQL also has a functionality for aggregating. So in this case, I want to find, again, for all the countries, the population. And then compose this query. You see, in SPARQL, using symbolic SPARQL, we always use composition to compose operators, because you could potentially have another aggregate after that. Yeah. And then, yeah, we take the sum and get this result. This SPARQL aggregate has an optional second argument, which allows you to group by the value of that argument, and that's what we're going to do here. Yeah. So we are going to retrieve for each country the population on the continent, and then we're defining an aggregate that groups by continent and computes the total population in that group, and also projects out the continent. And you can use the nice formatting of dataset. I think with that, oh, there was a question about IRIs and entities. Well, we are working on having IRIs for entities, yeah, which will make certain things more well-defined, because, for instance, if you have a triple of that form, say something like this, this is not actually RDF, because RDF says you need an IRI or a blank note in subject and predicate position. Yeah. While here we see entities, but in principle we can solve that issue by saying, well, we can assign an II to each entity and each property, and then just consider having entities and properties here to be syntactic sugar for IRIs referencing those same things. So that will make those things more well-defined, but the interaction between IRIs, RDF, and entities is very experimental, so we're still working on that. I think with that I'm going to close. Maybe, Andrew, are there more questions?
No, not that I've seen. I think it was just the one about the alignment between the IRIs and entities. Great. So thanks, Andrew, for helping me with those questions. And thanks, everybody, for listening. And I hope you liked it. You liked the new functionality. And if you have any questions or suggestions on how we should prioritize our future work on this project, well, let us know. Thanks.